We made carne asada nachos.
Oh, nice.
Nice.
Okay. So, good morning, good morning, good morning. Yesterday we talked about rational functions, talked about finding particularly the x-intercepts and vertical asymptotes. So why don't we start there with a little reverse review. So let's say we've got a function and we have a vertical asymptote at x equals 5. We have another vertical asymptote at x equals, let's say, -2. And then our function, let's say, has a horizontal asymptote. We haven't talked much about those, but you need that horizontal asymptote today at y equals 1. So it's leveling off at y equals 1. And then when we look at the actual graph, it's got an x-intercept at -4. So that's happening at -4. It has another x-intercept at, let's say, 3, and no x-intercept on this side. So let's say we have a rational function that looks like that. Now we don't know what this y-intercept is, and right now I'm actually not going to worry about that y-intercept. Yeah, we're just going to worry about the x-intercepts and vertical asymptotes. So we have our vertical, well, let me do that. We've got our vertical asymptotes at x equals -2 and x equals 5. What do those, and I want you to take a minute, think about what do those tell us about how our rational function has to be built? We have x-intercepts at x equals -4 and x equals 3. What does that tell us about how our function has to be built? And then we'll talk about that that horizontal asymptote in a second.
Well, the zeros have to be 4 and -3.
Well, the zeros are technically -4 and 3. The factors of something have to be x plus 4 and x minus 3. So
That's same thing with
right?
same thing with the vertical asymptotes, right? So you have to have x plus 2, x minus 5.
Yep, we got a factor that's representing a factor of x plus 2 and a factor of x minus 5. But where are those factors?
So the vertical factors become the denominator and the x-intercept factors become the numerator.
Okay, so there's an x plus 2 in the denominator. There's an x minus 5 in the denominator because those are creating the vertical asymptotes. Okay, happy with that. You said the x-intercept u1s are in the numerator. So there's an x plus 4 and an x minus 3 in the numerator. Okay, so those two factors in the numerator are creating the x-intercepts. Those two factors in the denominator are creating the asymptotes. Questions about that so far? I mean, that it sort of doesn't have to be any more complicated than that. Now, we do have to make sure about that horizontal asymptote and maybe talk about that y-intercept at some point. But we know these factors have to be there because we see those blue vertical asymptotes and we see those purple x-intercepts. That means these factors must be there.
I have a question then.
Shoot.
So I was looking back at some of the problems we did yesterday, and there was one where we found the horizontal asymptote. Well, you told us what it was, but the bottom term was only a binomial. It's x squared minus 9. It's missing that middle term. Does that have anything to do with it?
Essentially, no. The fact
Yeah.
that denominator is a second degree polynomial is what's important. Whether it has a middle term or not is determining the particular zeros.
Gotcha. I don't know if that had any effect on where the y asymptote would be.
Not any more than that 9 does. And actually, for the horizontal asymptote, no effect at all. The horizontal asymptotes, because they're end behavior, essentially, only the lead terms matter. Nothing else does.
That makes sense.
So, speaking of horizontal asymptotes, if we were to multiply both of these out, we'd have x squared plus x minus 12 over x squared minus 3x minus 10. So that's what it would look like in its polynomial form or its multiplied out form. And I want to look at that what happens when we look at horizontal asymptotes and why horizontal asymptotes end up where they are. We talked a little bit about it yesterday. But remember, the key is that horizontal asymptotes are an end behavior argument. I'm going to say an end behavior thing. So the horizontal asymptotes, notice this horizontal asymptote at y equals 1. This graph passes right through that y equals 1 location. We often think about asymptotes as lines you approach but don't touch. And actually touching an asymptote is perfectly fine. Asymptotes tell us about what happens in long run behavior. So it tells us about what happens as our x's get large positive as we head towards positive infinity and large negatives as we head towards negative infinity. What happens in between, the horizontal asymptotes don't care. So essentially, to figure out horizontal asymptotes, we want to imagine what happens as x becomes large. What happens to large x's? So we talked about this a little bit yesterday, imagining putting in values here. If we put in a value, it doesn't even have to be all that large. If we put in a nice value of x equals 100, I'm only picking 100 because it's easy to square and cube. I'm 100. 100 squared is 10,000. So this x squared here is going to be 10,000. So what's 10,000 plus 100 minus 12? It's still about 10,000, right?
1,088.
Which is about 10,000, right? And that's the argument here. For large values of x, these other terms don't make that much of a difference. Fair? Same down here, the 10,000 minus 300 minus 10. if somebody said, okay, you know, I'm going to give you $10,000, but it's going to cost you $10 in a fee, and then you're going to lose $300 because of taxes, you're going to go, woohoo, I get $10,000. You're not going to go, oh, I get $9,690. You're going to go, woohoo, $10,000. And then it's going to be a scam, so don't do it. But still. So this is going to turn out to be, for large values of X, about 10,000 over 10,000, and 10,000 over 10,000 is 1. Hence this thing leveling off toward 1 as we get larger and larger values of X. Now, if we went even bigger with that, if we went to say 1,000 for X, 1,000 squared is 1,000,000. 1,000,000 plus 1,000 minus 12 is even closer to 1,000,000 than whatever it was before was close to 10,000. And 1,000,000 minus 3,000 minus 10 is even closer to 1,000,000 than the 9,690 was to 10,000. So the larger it gets, the closer and closer those numbers get to being essentially the same numerator and same denominator. So whenever we look at, that's weird, why did that happen? No, there we go. Whenever we look at end behavior, just like we did for end behavior of polynomials, we really don't look at the rest of these terms. We just focus on what's happening with these lead terms. And the ratio between those lead terms, 1x squared over 1x squared, is 1. That's what gives us our horizontal asymptote. Now, if we were to graph something like, say, y equals 5x to the third plus 2x minus 1 over, say, I don't know, about 10x to the third minus 2x squared plus 5x minus 4. Now, if we wanted to find vertical asymptotes, we'd have to find the zeros of that denominator. If we wanted to find x-intercepts, we'd have to find the zeros of that numerator. But if all we were worried about was its horizontal asymptotes, all we would look at is these two first terms. Pink is tough on top of the orange. We wouldn't care about these. They don't contribute to the end behavior. They contribute to the wiggles in the middle. So what would our end behavior look like? Well, our end behavior would look like essentially 5x to the third over 10x to the third. We could imagine those, no matter how big the x value is, those are going to cancel, and we're going to end up with 5/10 or 1/2. So this would have a horizontal asymptote at 1/2. So we often say we get a horizontal asymptote at the ratio of the lead coefficients. If the lead coefficients are both 1, it's just 1 over 1. Horizontal asymptote at y equals 1. Lead coefficients of 5 over 10. Horizontal asymptote at 5/10. If we had y equals 3x to the 5th plus a whole bunch of stuff, as long as that stuff is smaller degree, over 7x to the 5th plus a whole bunch of stuff, as long as, again, that stuff is lower degree, as long as the 3x to the 5th and 7x to the 5th are our lead terms, we're going to have a horizontal asymptote at 3/7. Well, y equals 3/7.
So for it to be 0, then your lead coefficient would have to be a negative, right? On one of them.
No, if our lead coefficient, say that was a negative, then that would just be negative 3/7.
Well, no, but I mean, like, say, how would you have an asymptote of 0 then? Because I know we've seen it in our graphs sometimes.
We have, and we've also seen at least one that didn't have a horizontal asymptote at all. So what is the same about each one of these that's making this happen? What am I rigging in each of these to make this okay?
The degrees are the same.
Perfect, Aaron. The degrees are the same. This has an if the degrees match. If the degrees match. Because the only reason that those x to the thirds didn't matter here is because they were both the same x to the third. Fair? As a counterexample, what if we had, say, y equals 5x to the, well, let's say 5x squared plus 2x minus 1 over, say, how about 8x to the third plus 4x minus 7. And we have 4x squared. Doesn't matter what these, what the 2x minus 1 and the 4x squared minus 7, doesn't matter what those are. I'm just kind of making something up there so it looks like there's something there, but doesn't matter what they are. End behavior is a lead coefficient argument. So essentially, these don't matter, those don't matter. What we're comparing is that 5x squared and 8x to the third. So what's going to happen to 5x squared over 8x to the third for large x values? Well, let's use our examples here. We were using x equals 100. At x equals 100, 100 squared is 10,000. That numerator becomes 5,000. And 100 to the third power is 1,000,000. So it's 5,000 over 8,000,000. What's 5,000 divided by 8,000,000? Sorry, 50,000. At x equals 100. Still, doesn't matter. What's 50,000 divided by 8,000,000?
An infinitesimally small number.
Yeah, something tiny, right? We could even cancel a bunch of those zeros out if we want. So those 4 zeros and these 4 zeros, it's going to be 5 over 800. Okay, still tiny, right?
0.000625.
Super tiny. So what's happening to this function as those x's become large? It's heading toward 0. So because the denominator is of higher degree, because the denominator is stronger, the denominators are going to be higher values in ratio. High values in denominators make us small, make us go towards 0. So this ratio of the lead coefficients happen if the degrees match, but what if the degrees don't match? If the degree of the denominator is larger, then it's going to shrink everything down. Going to have big denominators with numerators that can't compete. So if the denominator is larger, we always get that horizontal asymptote at y equals 0. So a lot of these will have, Andrew, those horizontal asymptotes at y equals 0, because anytime the denominator is larger in terms of degree. Anytime the denominator is more powerful, zeros out.
That makes sense.
What do you think happens if the numerator is larger?
Does it trend towards infinity?
Yeah. So if we have, say, 3x to the fourth plus, again, stuff, as long as that's the lead coefficient, lead term, it doesn't matter, over even a larger value, say 11x to the third plus stuff. That x to the third can't compete with the x to the fourth. Even a value like x equals 10, at x equals 10, you're going to have 3 times 10 to the fourth is, well, again, 10,000, so that's going to be 30,000 over 10. Okay, 10 to the third is 1,000. 1,000 times 11 is 11,000. So even at a comparatively small number like 10, this thing is not a large number, but a comparatively good sized number at 3, as opposed to our 0.00000, whatever that was.
Oh, 3 times bigger.
Yeah. If we go to 100, watch what happens. 100 to the fourth. It's 100 to the fourth. How many zeros does that have? 2 zeros to the fourth gives us 8 zeros. So 300 million over 11 times 10 to the third. 10 to the third. Sorry, 100 to the third. So 2 zeros times 3, 6 zeros. So 300 million over 11 million is 300 elevenths, and 300 elevenths is about 30. And the larger the value for x, the larger this is going to get. Now, it's not a crazy large value. That's because this is only 1 degree higher. But imagine if that was x squared instead. That would have been over 110, which would have made that 3 a lot larger. This would have been over 300 million over 11,000, which would have been a very large number. So our 3 rules, if the degree of the denominator is larger, zeros out. Denominators want to make things small. So if the denominator is more powerful, zeros out. If they match in power, then they're going to have a fight on their hands, and that those lead coefficients determine the ratio of our horizontal asymptote.
So for that one, basically, like if it's 1/2, then our horizontal asymptote is at 1/2.
Yep.
Right? Okay.
Yep. It's just the lead ratio of those lead coefficients.
So even if it's something crazy, that's exactly what it is. Like 11 over 17, it's just going to be right there.
Yep. Whatever. If this is A and that's B, our horizontal asymptote is at Y equals A over B. Whatever they are.
Gotcha.
If the degree of the numerator is larger, essentially if the numerator is more powerful, we simply have no horizontal asymptote. It is growing without bound. Nothing is constraining it. The numerator is becoming super big. The denominator is trying to pull it back down, but isn't strong enough. And it just goes off either to positive or negative infinity, depending on the end behavior. Now, there's a good part and a bad part to all that. ideally, the good part is that it's not as bad as it looks. The bad part is it can kind of look bad at first because it looks like there's a lot of information there. But if we had, say, x squared minus 3x minus 10 over, say, 4x squared minus, what do I want there? Yeah, 16. Why not? And we wanted to talk about what are the x-intercepts, what is the y-intercept, what is the horizontal asymptote, if any, what are the vertical asymptotes, if any, and what's the, actually those are all I want. Yeah, x-intercepts, y-intercepts, because we always can find x-intercepts to y-intercepts. Because it's a rational function, it might have horizontal asymptotes and vertical asymptotes, so we want to find those if there are any. So we have our tools now to find each one of those things. And those are our 4 major characteristics of a rational function. Crystal, which one of those do you want to start with?
I mean, might as well just start at the top.
All right. So Crystal, what causes our x-intercepts? What do we look for?
Our x-intercepts are the x squared minus the 3x minus 10.
So you said the zeros of the numerator.
Yes, that's what I said.
That's what I heard anyway. That is what you said. You said, we'd use the x squared minus 3x minus 10, and what would we do with it? We'd set it equal to 0 and solve.
Both of those factor fairly nicely too.
Well, that's because I'm a good guy today.
How nice of you.
So yeah, it's nice when these factor. We're going to get what? Minus 5 and plus 2 equals 0. So our solutions are going to be x equals 5 and x equals negative 2. So what does it look like our x-intercepts are?
5, 0 and negative 2, 0.
5, 0 and negative 2, 0. Okay. Aaron, which one do you want to do next?
Let's do the vertical asymptotes.
Okay. So, vertical asymptotes. How are you going to find the vertical asymptotes?
They'd be the zeros of the denominator factored.
Good. Zeros of the denominator. And even if it doesn't factor, we can find the zeros, just quadratic formula, rational root there, and we got all kinds of other tools. So we're going to take the 4x squared minus 16, set that equal to 0. So going to factor that out because why not? And we're going to get x plus 2, x minus 2. So our solutions to that equal to 0 would be plus or minus 2. Okay, what does that mean about our vertical asymptotes?
All right, quick question.
It's
Before we
probably
go
a good question. What's that?
So you can also factor that as 2x plus 4, 2x minus 4. But that changes your...
Well, you could factor it into 4x plus 8 and x minus 2.
Yeah, so how does that affect your...
Or 2x plus 4 times 2x plus 4, right? That's what you said?
Or 2x minus 4.
Minus 4, yeah. So that would mean 2x plus 4 equals 0, which means 2x equals negative 4 divided by 2,
Gotcha.
and you get x equals negative. Doesn't affect it at all. It just makes it
Okay.
harder. Yeah.
I see what you did. Cool. I was just curious, so what multiple ways to factor, how does it affect it?
It doesn't, because we're trying to find a 0, so the extra factor, essentially that 4 doesn't do anything for our 0. Whether it's in one of them, whether it's in both of them, wherever it is.
Yeah, because it wouldn't really matter what form it's in as long as it's been factored correctly. You still plug the 0 in and it's going to affect it the same way.
Yep. Absolutely. So that would make it look like we've got a vertical asymptote at x equals 2 and a vertical asymptote at x equals -2. But what do we notice that we had to be careful of from yesterday?
The same
Oh.
factors on the numerator and denominator.
What does that mean is going to happen to that x-intercept and that 0? Vertical
Means-
asymptote.
One of them's going to go away.
So the x minus 2, because it's a factor in both the numerator and denominator, it's not going to cause either an x-intercept or a vertical asymptote. Essentially, the x plus 2 factors are going to compensate for each other perfectly. They're going to balance out. They're going to essentially be a 1 all the time, almost all the time. And they're going to have no effect on the values of this function, except that we are going to have a hole at x equals -2. Because we're still undefined at I'm -2. So essentially that factor disappears from the problem, leaving that little hole at -2. And Aaron, that's one of the reasons it's nice to find the zeros of the top and then the zeros of the bottom right away. So you have both lists. And anything that occurs on both lists, it's dink, dink, gone. So I like that choice of doing those next. It's especially handy if you write it out that way. So like if you're doing this problem, a lot of people will factor them and write those factors out. And then you can see that, oh, wait a minute, I can see that these factors are the same. So this thing, this rational function is going to want to behave like y equals x minus 5 over 4 times x minus 2. But we have to be careful. These two functions are not equal. Why are those two functions not equal?
Because there's that coefficient of 4, right?
Nope, there's a 4 in both of them. F4, F4.
Because if you multiply them back out, they're not going to be the same thing anymore.
But yeah, they'll change degree.
What makes two functions equal?
The degree, right?
Actually,
Sort of.
no. What makes two functions equal is that if you put in the same x to both functions, you'll get the same output. So, for example, if we had 5x to the third over 7x to the fourth, I don't want 7, I want 15. 15x to the fourth, we could reduce that to, well, 1 over 3x, and those two functions would be equal. Any value you put in for x here is going to give you the same value as if you put that x in there. Those two are equal.
That makes sense.
These two are not equal. If you want to verify that, pick an x value.
So your x plus 2 still matters. It just has no effect on the graph, not the actual function, or not the actual polynomial.
That is a great way to look at it. Let's take a moment and do that. You guys, we played with Desmos some yesterday, right? So if we grabbed Desmos, you can't see it yet. Grab Desmos.
I would explain why yesterday you kept harping on don't cancel it. Just pretend it's not there.
So let's graph it. Let's graph the x squared minus 3x minus 3x minus 10. Oops. Divided by, I don't want that division. Fine. Parentheses it is. Divided by 4x squared minus 16, 4x squared minus 16. So that's the graph we're trying to look at. Get my chat out of the way. And we want to compare that to the one after we canceled out the x plus 2s. So the numerator is now x minus 5 over, and this is the one that's in blue, 4 times x minus 2. Now, for those to be the same graph, they'd have to be the same value for every x. Is that the case? Does it look like that's the case?
They look the same.
They look the same? You guys all going, oh, they look the same. This guy's talking crazy.
Is this a trick question?
No. A little bit. The reason that they're not the same function, the reason that they're not equal, is only because of that -2. This function here, the blue one, if we tried to evaluate it at -2, if I can get it, we'd get 0.438. At -2, we get that value. You plug a -2 in there, you're going to get what? -7 over -16. -7 over -16 is apparently 0.438.
So
What
basically, there's just no hole
There's no hole.
in the other graph.
This function, the orange one, same values everywhere except at -2. It has that hole in it. Fair? So are those two functions equal? Well, no. They're equal everywhere except at x equals -2.
So they're similar. They're just not equal.
They're equal almost everywhere, if that helps. Almost everywhere is actually a technical mathematical term and qualifies here. Equal everywhere except for on a set of measures a 0. As we talked about yesterday, that hole is infinitesimally small. But they're not equal. Except where they are, which is almost everywhere.
Yeah, because basically, right, that 2, if you put any amount of zeros and then a 1 after it, like in a decimal, then it's got a value.
Yep. And this one's got a value everywhere. Now, this is, we talked yesterday about what happens to computer programmers a lot. They will their scenario is modeled by that orange graph, and that's the data that's coming in. But in their math, they reduce it down to the blue function, and their blue function, when they test run their blue function, the values that they get come out and come in, and it's no problem, not causing any problem whatsoever. So they put their program into practice, and it gets information into it from the orange function. And as it's going along, running itself, it hits that value, and the whole thing crashes. The power grid goes down, the plane crashes, people die. It's horrible. Because the incoming data was following the model that had the hole in it. All their calculations were following the model that didn't have the hole in it, because they went on and canceled stuff. Fair?
So don't program -2 into the program. Got it.
Yeah, and all it takes is that line of code that says, if x is -2, don't use the function, let it be the value that fills the hole. And it just says, okay, if that x is -2, don't use my function, just use 0.438. Because that's what would fill the hole. It's actually referred to as a removable discontinuity, because you can remove the hole just by saying, oh, it's this, by the way. You'll talk more about continuity in calculus, for those of you going into calculus.
So, like, for this graph, like, say you were given this one right here, the top one. Could you say, like, how would you say that how the -2 is undefined in this one, right? But then once you reduce it, then you have a value. So is there any point in time where we'll have to like do something like that? Like, hey,
Yes,
find the value of the undefined from
absolutely.
this graph.
Week 1 in calculus. A lot of that in calculus.
Makes sense. So something good to remember.
Mm-hmm. But the nice thing is, well, how do we find that hole? Well, you do the reduction, get rid of the discontinuity, and then evaluate this. This thing at -2 is where the hole is in this thing. Now, it's often harder than that, but that's the idea. Get rid of the discontinuity and evaluate. You might remember back to the difference quotient, where the job was to get rid of that h in the denominator. That was us trying to get rid of a discontinuity so we could evaluate around it. Anyway, so we have our zeros of the denominator giving us our one vertical asymptote, and the zeros of the numerator giving us our one x-intercept, and we've recognized that at -2 we're going to have a hole. So, Justin, which one do you want to find next?
Well, the horizontal asymptote is 1/4, 1/4.
And that's the nice thing about horizontal asymptotes. There's very little work to actually be done. It's an observation mostly. So those of you who like mechanics to grab onto, horizontal asymptotes aren't great with mechanics, but it really is just something we're going to look at and say, okay, what is that horizontal asymptote going to be? Well, do our degrees match? Yes. If the degrees match, our horizontal asymptote is the ratio of those lead coefficients. So y equals 1/4. If the degree of the denominator was stronger, it would be y equals 0. If the degree of the numerator was stronger, higher in degree, we'd say there's no horizontal asymptote. And that's it for horizontal asymptotes.
The y-intercept is simply setting x equals 0, right? And then solving the equation.
Yep. Y-intercept. We know how to find y-intercepts. Y-intercepts happen when x equals 0. So let x equal 0. And particularly in this form, it's nice because that goes to 0, that goes to 0, that goes to 0. And we have negative 10, negative 16ths, which would reduce to 5/8. And
The majority of the time, the y-intercept is just the ratio of the constant term, right?
yes, as long as if your polynomials are in standard form, the y-intercept is almost always just the ratio of those constants. The only exception is when they don't, is when one or both of them don't have a constant term. So like if this was a 16 over x instead, then if you let x equal 0, you'd have negative 10 over 0, which would be undefined, which means you don't have a y-intercept. Well, you don't have a y-intercept because you'd have a vertical asymptote at that
Versus
point.
the other way, if you had 10x over 16, it'd be 0 over 16, then your y-intercept would be 0.
Right.
Gotcha.
So if we wanted to, say, graph this, I mean, I know Desmos can graph it for us, but part of our goal here is to, you know, be able to feel kind of where those graphs are coming from. We're going to have that vertical asymptote at 2, so a vertical asymptote at 2. We're going to have that x-intercept at 5, so x-intercept at 5, and nowhere else. That horizontal asymptote at 1/4. So that's at 1/4. So my y scale is quite broad. And that's all we're told. Well, I guess we also have the y-intercept, right? At 5/8. So y-intercept 5/8 is more than a quarter. So we are going to have a y-intercept right there at 5/8. And we have to draw the graph that goes through those points and is asymptotic at those places. So really, we either have, you know, as we come off of this asymptote, we're either going to go upward or we're going to go downward from that asymptote. Which one is going to happen here? Are we going to go upward on that asymptote or downward off that asymptote? Well, if we go downward through that asymptote, if at any point we go downward to be asymptotic here, we're going to have an x-intercept. And we don't have any x-intercepts down there, right?
Yeah, so wouldn't it be coming from the other side through the 5 towards the 2?
Yeah, and it's got to go through that 5/8, right? So it's got to be up there. It has no choice. Andrew, as you were saying, coming from the other side, you know, does it head upward or does it head downward? Well, it has to go through that intercept at 5, so it's got to go that way. So that is almost what this graph looks like. What's the only thing left we have to put in this graph?
What am I missing?
It's funny that you would say it that way. What
I feel
are
like
we
we
missing?
hit all the points. I guess we have a hole at -2, right?
Yeah. What we're missing is the point on the graph right there. You're right. We did have all the points. We didn't have the point we didn't have, though. These are the jokes. Now, when we looked at Desmos, we didn't see that hole. If you graphed it on your calculator won't show that hole, but that hole is an important structure here. So when we graph it by hand, we kind of want to show that hole. Actually, we really want to show that hole. Show that hole. Cool. Crystal, is this better than yesterday? I know you were fighting with this a bit yesterday.
Yeah, for whatever reason, this is a lot better, or maybe my brain is just more receptive to it on day 2.
It generally, at first, I find with this particular section, at first it's like a lot of information and like, where does all that come from? And then after a while, it's like, oh, okay, just that those come from there, that comes from there, those are that, and okay. But it takes a little bit of processing. It takes kind of looking at it in pieces and then putting the pieces together as opposed to trying to look at it all at once.
Agreed.
So I just had a thought, right? So say we were given this graph, like we didn't know any of the stuff above it. We were just given this graph, right?
Mhm.
If it had like say that hole was at -3, right? So we could automatically assume that one of our factors on top and bottom would be x plus 3.
Yep.
Which would be how we would factor out the rest of the polynomial. Like if it was like a 3rd or 4th degree polynomial.
Yep.
That makes sense. It's just like I'm trying to figure out like how they're going to word problems that we run into here,
Oh, yeah.
and I feel like that would be one of the things that we'd have to pay attention to figure out at least one of our zeros.
If you have a hole, that means it's on both top and bottom. If you've got the vertical asymptote, that means it's on the bottom. If you got the y-intercept, that means it's on the top. So x minus 5. If you have a horizontal asymptote that's anything other than a 0, that means that's the ratio of the lead coefficients. That's going to have a 1. That's going to have a 4. Multiply everything together, and boom, you got a pretty polynomial.
That makes sense. So like even if we didn't have the graph and they were like there's a hole at x equals -3, then we could use that to figure out the rest of the factors for the polynomial.
Yep. And that often happens when you're trying to model something like, okay, my function doesn't exist at this location. That's the hole. My function tries to infinity out. It has that vertical asymptote behavior at this time, and it bottoms out at the 5. And, so if you have kind of information about how it's behaving, you can build the model from that description of how your data is behaving. And that's common to have to do. All right. You guys good with all that? Go practice that, and go practice your, figuring out what the graphs look like for polynomials as well. We're going to kind of put that all together and play with some cool stuff tomorrow, and then we'll be getting ready for your test on Tuesday, I think.
It's like for our test, what kind of problems are we going to encounter with this? Will it be like we're given the polynomial and we have to solve the graph, or is it the other way?
Horrible. Oh, they're going to be nasty. Oh.
I feel like that's probably not wrong.
There are problems on my long form of that test. I think the long form's got like 25 questions or so. Way too long. There are both. There are ones that say, here's the equation, find all the pieces. There are some that say, here's a graph, find what the parts have to be so you can make the equation. Because of the format we're in, this is in some ways a little bit better of a question, because, technically with this, you go, none of you guys would do this, of course, but you go online and you can have all this stuff described. You can plug this into certain websites or software, and it will show you what it looks like, and you can figure out what the answers are.
Like Desmos?
For example, yeah. Going in this direction, it's much harder to take a screenshot and upload that into something that's going to tell you where the zeros are. So in some ways, that's a better online question, where this is a better handwritten test question.
That makes sense.
But if you make this a 7 instead, then those x-intercepts are irrational numbers, so they're coming from the quadratic formula instead. You have to give exact values, so you're dependent on those hand skills again.
Gotcha. Makes sense.
Go play with those. Anything you guys need, let me know.
Thank you.
You're welcome.